As you can read, I'm Marco Balduzzi. I'm pretty happy to be here. So I just realized that my first talk at Hacking the Box was in Kuala Lumpur in 2011. So I'm happy that I've been participating in this event since 12 years, and the conference has not lost its authenticity, and it's a great platform to present research like this one. This is a work I did with a few colleagues from Celada. This is a partner we work with because computer numerical control machines are kind of huge equipment like this. So we don't own machines. So when we started research, one of the first issue was, okay, where do we get the machines? So I spent like 2 months to look for a partner. And we managed to get access to real-world physical machine like this one, and that we use for the experiments. So these machines are very important and very prevalent, so you can find them everywhere. And they consist of a wide diversity of machine tools. So there are drills, lattice machine, mills, grinders, and so on and so forth. And as you can see, and you can imagine, they are very expensive. They are very complex in terms of how they are made and how they operate. And they, of course, play a very critical asset for the safety, both the safety of people and the security of a company that use them. And this, by per se, justify the research. On top of that, no one before us looked into this direction. So we decided to jump and see what's going on. So this is a preliminary, my opinion, is like a first step into this direction. So we just scratch the point of the iceberg. But if you guys are interested into this sort of domain as well as industrial robots, there is a lot to look at. I mean, the attack surface is huge. Okay, so this is just some of the things that could potentially go wrong. All of this because this machine nowadays are, as you can guess, are connected, right? So we have IoT and we have this, this nice buzzword, which is industrial IoT, right? So this machine tend to be connected to the network, both the enterprise network as well as the production network for different reasons, like managing the machine, controlling the machine remotely to do a bunch of things, collecting the data for improve the business, and so on and so forth. Of course, what could go wrong here? A lot of things. So the talk is about these potential threats. On top of that, the supply chain behind CNC machine is pretty complex, in the sense that most of the vendor that develop CNC machines, which are here, the machine manufacturer, they actually do not develop the controller. All right, so it's a bit like in the car industry. What happens is that often you have basically a vendor that develop the engine, and the engine is basically sold to a car manufacturer that develop the car. So here it's exactly the same thing. And what usually happens, you have the NC, which is the controller. So the NC manufacturer develop one controller, and often that controller is used by 10, 100, or even 1,000 of machine manufacturers to produce machines. Then, of course, this machine get resold to a local reseller, and then, thanks to the integrator, they end up in the end user that use the machine. So in a such complex supply chain, there are a few interesting considerations to be made. First, if there is a bug here introduced by the NC manufacturer, this bug get propagated along the supply chain up to the end. The second, if there is a technology used here, let's say the NC manufacturer decide to use a proprietary protocol, then the machine manufacturer need to use that proprietary protocol, and so on and so forth. So the technology get propagated all around the supply chain. So for that reason, we decide to focus our research here at the beginning of the supply chain, because if there is a problem here, this problem most likely will go to hit basically all the machine manufacturer, reseller, integrator, and end user. On top of that, while there are a lot of machine manufacturers, a lot of vendors, a lot of names, there are not many vendors of controllers, which makes it a bit easier to conduct an assessment that makes sense. What I mean is our goal is not just doing vulnerability research and find vulnerabilities, but do a kind of survey and study of the threat landscape of a CNC domain. So we want to be as much representative as possible. So what we did, we pick up 4 vendors, which represent a consistent amount of all the controllers that are out there. And these vendors are huge. There are 2 vendors that are Okuma and Fanuc from Japan. Japan has always been a leader in this domain, so these 2 vendors makes really a lot of a market. Then we have Hijacking, is a vendor from Germany. It's probably the largest vendor of NC in Europe. And then we have Haas, which is a vendor that is also behind the Formula One. So if you are into Formula One, like Grand Prix, they also have a team. It's the same vendor. And all of this, if you can see from the number, they are quite huge. So we are talking a company that have more than $1 billion revenue. Some vendors produce controllers and machine. For example, if you take Haas, they go with both controller and machine. Some other vendors like Hijacking produces controller and not machines. Okay. So here in the table, you can see that we used both simulators to run our experiments, often in the first phase of the research to avoid basically to crash the machine and even to make our life easier, because with simulator you can do some experiments in the lab without needing to go down to the factory. And then we also test everything on real world machines. Usually we have 1 machine per vendor, apart from from Fanuc, where we test on 2 machines. Of course, since the problem we have identified belongs to the controllers, all the machines that get manufactured with that controller are vulnerable. So this is the interesting part here. So this is a photo that gives you an idea of how a controller simulator looks like and how a real-world machine looks like. So there are 2 types of controller simulator. One, which is virtual. For example, Hijacking has a virtual simulator that basically runs on top of VirtualBox, and you can run it on your computer and you're ready to go. This one is a physical simulator and is exactly the same that gets installed on the machine. The only difference is that the peripherals are emulated. Okay? So, but the software and the logic and anything else, it's basically the same. So, we use controller simulator in all our experiments in the first phase, and then we went to with real world machine, with the exception of Fanuc, the last one on the right, in which we implemented the tags directly on the controller, on the machine itself, because we didn't have a simulator for that. Cool. So, what about the research approach? So, which kind of path we take in our research? So, we try to be as neutral as possible, to not finger point again a specific vendor, and we try to use the same approach also to compare which vendor most likely is more problematic compared to other. So we did an initial scraping with automated tool like Nessus, and you are security experts, so I don't need to go detail here. So phase 1 is only to get rid of vulnerabilities that are not related to the technology itself. What I mean is that some of these machines run, for example, Windows with some service that could be vulnerable. In that case, is a problem of the operating system and not of the specific technology related to CNC machines. So after we got rid of these generic bugs, okay, which doesn't really make some, a discrimination between CNC machines and normal computer, we took a look at the technologies that are domain specific. Here you have a table of some of these technologies that are more than those one. These one are those ones that we consider in our research. So those ones that I call default technologies are those ones that are installed on all the simulators of a vendor. For example, Haas come with MTConnect and Ethernet Q commands. I'm going to show you an example of those one by default, okay? While other are optional in the sense that you can if you, is an add-on. Basically, if you want to have support for example, MTConnect on Akuma, you pay on top and you get access to that one as well. So let me give you an example of how this technology looks like. For example, in case of Haas, this is an example of Ethernet Q commands. It's a proprietary protocol that has been designed by us to remotely interact with a controller. So what you can do, you can connect to the controller and maybe ask to the controller, okay, what's your serial number? Or how many pieces are produced, and so on and so forth. Of course, you can also, this protocol is used to monitor the machine. What makes kind of weird is that you can also query variables out of the memory. So there are memory blocks basically here. And for example, with this command, you can say to the machine, okay, give me basically the value of variable 10,000. I'm going to show you later what does it mean with this. And what is even worse and strange, you can also write to certain memory location, okay? Which is already here, since you are a security expert, you come from that domain, you might already think what could go potentially wrong here. Another protocol which is very well established in the domain and is the opposite of our one. So it's not proprietary, but actually goes with the direction of try to make the machine talking to each other, is MTConnect. What does it mean is that each vendor speaks his own dialect. For example, this vendor for a certain command use a specific terminologies, while MTConnect is basically an effort to standardize all the different protocols. So this is one of a protocol we also consider in our search, and is very prevalent. All the machines support it. After we have made our due to diligence in understanding which kind of protocols are used in the CNC domain, we did threat analysis. So we put ourselves in the shoes of an attacker with a black hat, and we said, okay, what could go potentially wrong here? We developed some scenarios, and then we developed POCs of attacks that we tested on the real world machines. We found vulnerabilities that we then reported to the vendor with the support of a cybersecurity and infrastructure agency in US. Which was very helpful in the responsible disclosure process that I'm going to detail later on. It was not easy. Cool. So let me give you a kind of summary of overall of the macro categories of problem that we have identified, and then we go deep into, of course, a bunch of examples. So these are the macro problems. So legacy software. Okay, this is kind of obvious, right? So you have seen probably. Many people today have told you that ICS technology, also IoT technology, comes with a bunch of legacy software. As a result of that, we were able to leak information out from this machine in different forms. Often there is a lack of authentication, or authentication is not enabled by default, which is kind of surprising in 2023. There is also often a lack of resource access control. So you can, if you have access to a certain memory region, you can easily have access to our memory region. So there is no separation of memory addresses and the file system and, usual things that in the operating system are there since more than 20 years. So let me give you some example. For example, here, this one is a dump of some data fetch via MTConnect. So the protocol I was mentioning to you before. This one is again the effort to standardize the different protocols. So in JSON, you can get, in XML, you can get basically information on what the machine is doing, like the position of the axis, how many pieces are produced, and so on and so forth. Problem is, as you can see down here, is that a certain vendor exposed that piece of information that is the line of code that is currently executed on the machine. So these machines are programmed with some with software, so with programs developed in G code. So that's the name of the programming language, and that is the instruction line that is currently executed on the CNC. So as a result of that, you can, easily write a crawler that basically query the service over and over, and basically fetch all the instruction that get executed. So with the ability to leak the source code of the program that is running on the machine. So you can already understand what could go wrong, right? If you have an attacker and you can dump basically the proprietary code that is executed on the machine. In another example, we found that one of the controller had the jumper that allow to boot an SD card enabled. So as a result of that, we were able to dump the firmware. So this device come with this board from Seco, is an Italian vendor, and there is a jumper called Jumper 27 that allow you to specify from which device you want to boot. And if you set it in a correct way, you can boot from the micro SD card. So as a result of that, you can basically boot a kind of a live CD made with U-boot. In this case, the vendor had a bug in which they were leaking basically the bootloader in their Git repo. So we managed basically to boot the controller with our micro SD, patch the system, and then we were able basically to SSH in the machine. We use this trick to be able to debug some of our attacks because we had at the point like a footprint on the machine for debugging the logs and so on and so forth. But the thing here is the vendor, even when we talked to them, they told us, where is the problem? I said, you don't see the problem. I mean, anyone can basically dump the firmware of your CNC machine that cost $100,000. And we said, okay, yeah, maybe there is a problem, right? So they really don't get it. So I will get on this after at the end of the talk, but they don't really see the necessity even of protecting their code, right? The code running on their machines. Another issue is the lack of resource access control. For example, here is an example on Haas. Haas use the protocol I was showing you before, where you can write on certain memory addresses. And the manual says that you can write certain variable. These are the variable used by the program to operate, so the local variable of the program. The thing is, you can also, from our experiment, you could also write to variable that belong to system operation with the result of influencing what the machine is doing. So here I have a demo on a machine that is working, is supposed to work in debug mode, which is called single step mode in the CNC machine. So single step, it means that the machine runs, here you have like the source code of a program get executed. It go by instruction, like when you are debugging a program, no? And the operator need to push a button on the controller to step through the different code. And what the attacker does, it basically overrides system variable that control this single step mode. And basically the machine run all the code to the end. So you can imagine what happened. If you have an operator there, it's debugging things, and then you made basically the machine running all the program that could contain like issues and cause of safety basically to the operator, and potentially also breaking the piece. So let me see here. So you see here you have a graphical representation of what the machine is doing. So, and the program is moving, see? So simply an attacker, look, by basically connecting to this service and overwrite a global variable, it will basically make the program go to the end, crashing basically the machine and creating some safety issue to the operator. This is just an example. So the impact of all of this is huge. So this is basically the table we came up with. So for the different vendors, we basically came up with 5 attack classes. So the classic compromise is based on its own, because as I was saying before, this one is related to bugs on the software running, maybe on the Windows operating system running the CNC. And then we have attack classes that are damage. So damage basically of the piece under production or of the machine under production with cost that you can think could be like easily like thousands of euros, because this machine is super expensive. Denial of service, like making the machine basically not working. And if you think that the companies nowadays might produce, I don't give a name, but there is a vendor in Italy, they claim to produce a machine every like a car, every 7 minutes. So if you block, of course, the operation of this production line costs like a lot of dollars, right? So a denial of service here is a critical, is a main problem compared to maybe traditional environment like networks. Then hijacking, it means to take control of what the machine is doing and influence the machine so that the machine can produce something different from what it's expecting to produce. And then theft, which could be theft of production information, program code, taking a screenshot, and so on and so forth. So what happened here is that pretty much all the vendors are equally vulnerable to all the attacks, as you can see. So it's, as we were saying before, this is just the point of the iceberg. So in the future, I'm expected to see more and more attacks in this domain because there are really issues everywhere. So let me start with a simple compromise. So here is a simple example in which we use Metasploit to leverage a very old vulnerability from 2010 to install a plugin in the controller itself. So this is an Okuma controller. So Okuma comes with a possibility to extend the functionality of the controller, similar to plugins for your browser, for Chrome, right? So, okay, it's the same thing. So you can develop app, and you can lure your victim to install this app, which could be a malicious app in this case. You can either use a vulnerability to install the app. You can send the app and use some social engineering tricks. You can put the app on the store. They have an app store called, I think it's called MyOkuma, and you can pretend to be a legitimate app and you upload your malicious app. So normal things you might understand by yourself. And in this case, we compromise the controller with this very old vulnerability. We install this malicious app. And then this malicious app worked as a backdoor. So as you can see here in the video, it will basically connect back to our command and control server, reporting which controller has been infected with IP address and information on controller, like the name and so on. You will see later on. And then at that point, the attacker can connect in, and basically ask the machine to do whatever he likes. It's very simple. You can see here. So this is the name of the machine, the serial number, a type of controller that is running. Server IP. At that point, the attacker can connect in and change some variables. So this is a variable I was mentioning before in the memory space. You will see later in the presentation. Of course, this is an example of how an attacker can take control of a controller. There are different problems here. Of course, you can run a botnet. But the problematic things here, you have access to all the information of the controller itself. So not only of the operating system, but also of what the machine is doing, and also influence what the machine is doing. And I will show you some now example of different attacks we manage to do, from different angles. So one is about how to influence the geometry of the tools. So these attacks are all specific to CNC machines. So here what we did, we developed a program that was supposed to drill some holes that are 5 millimeters deep, in some piece of metal, which is this one here. So the machine moves. I have also the video. You can Google online, you find it. The machine moves and basically carve 5 millimeter depth, right? And so what the machine does, it has basically, this is the list of tools installed on the machine. Tools number 1 is configured to be long 8 centimeter. That's the name of a drill bit. And then there is something called compensation. So what happens is that when the machine operates, basically the drill bit wastes itself, because more holes you do, more basically reduce in length, no? Because you are basically wearing or consuming your driller, no? So the machine basically automatically compensate that effect. And you as an attacker, you can influence this compensation parameter called where. So in this case, the attacker, you can see top right, he connects to the service and they abuse the service by introducing a compensation of 0.25 millimeter, which is nothing. So as a result of that, you can see in this slide, This is the error-free, so what the machine is supposed to do. So drilling at a depth of 5.05 millimeter. After the attack, the machine basically with the same code, so without changing the program, but just influencing this wear parameter, the machine will add basically a depth of 4.80. So as a result of that, an attacker can cause micro-defects in the production. So if you are a company that is producing millions of pieces, you do an attack like this, it's very subtle because it's very difficult to detect from QA. And imagine that this machine operates at 0.00001 millimeter, 10 at minus 5 millimeters. So here we use 0.25, which is a lot, but you can go down in scale as much as you want. So if an attacker can introduce these micro defects, he can basically ruin the production of thousands or a million of pieces that get to the market, and then, the company has to recall those pieces back with all the associated costs. So this is a real problem for manufacturing. So a variation of this example is this one. You can already read on the title what's the goal here. The goal here is to damage either the tool, which is the point of a drill, or the part that is being produced. So for that, since this drill bit, like this one, so the normal one in this special metal, they cost really a lot. We didn't want to break one of those ones. So we 3D printed with a 3D machine a point in plastic. And then we did the attack. So in this case, we set a wear of minus 10, which is 10 centimeter long. So we basically say to the machine, look, your tool is not anymore long 8 centimeter, but is long minus 2. And at that point, the machine compensate and go down and crash completely the point against the metal, and the point get basically broken. So you can see the damage here. Another issue that I've already anticipated before to you guys is how you could potentially leak program code. There are different variations of this attack. This is the most common one that we have found. So by abusing a data leak in MTConnect, we wrote a simple Python script that recursively query the service over and over while the machine is running. So as you can see here, every dot is every time the script query the service, and every V is every new instruction that the machine is operating. So here you have a machine that operates. Here are the different line of code of the program. As you can see here, the attacker is able basically to leak the program executed on the machine. So this as well is a super severe, because this is considered, of course, a proprietary code, because if you can leak or steal the program executed on the controller, then basically you can implement or build basically the same piece of your competitor, no? So you can see here the issue here with leaking that piece of information. In addition, G-code, similar to other programming languages for CNC machines, is not compiled. So if you leak the code, you don't even need to reverse engineer it. So you have basically clear text all the instruction. So this is super severe, and this one got, of course, fixed immediately. It's probably the vulnerability that got fixed as first, because it was pretty clear to everybody that we had a problem here. This will also bring to our next attack. As you can see here, I have highlighted this one in red. That means what? It means you, that are your driller, right? Drill 2 holes, you can see here in blue. So what happens if this one is a parametric program? So G-code has the ability to use basically, like in normal function of our programming languages, use parameters. And this is made because when you are producing and you want to produce like some variation of your piece, you can influence the production. So you can say, okay, now you drill 2 holes, then you drill 3 holes, then you drill 25 holes. Or if you are building a piece which belongs certain centimeter, you can say same shape but longer, shorter. So you can influence such parameters, such program remotely using a controller, which is okay, it's a nice feature. But of course, it can be abused. So if you are an attacker, and you're able to dump the code and understand what the code is doing, then at that point you can connect to the machine and say, do you know what? Let's change the variable number 1 from value 2 to value 5. So at that point, the machine change completely of behavior and start basically producing a piece that instead of having 2 holes, have 5 holes. Of course, an attacker, this is an example, but an attacker can do anything. So if the thing here is that such variables are exposed over the network, and an attacker can basically influence the behavior of the program. So hijack basically a parametric program. Then another attack is called program rewriting. So this is a FANUC. This is one of the vendors that we test directly without having a simulator. So this machine cost really a lot of dollars, and it's FANUC. It's one of the probably most and top used controllers in the world. So here you have a program that gets executed. It's called 0,1000. Right? Here you have information on the position of axis, X, Y, Z, B, C, and a few other parameters. Here we wrote a malicious client that basically can connect to the services, download the program here. So we dump the program, we open up the program, we change the program, we re-upload the program. And what the machine does, it automatically substitutes the previous one with a new one without informing the operator and nothing. So an attacker can basically take control of the machine and reprogram the machine with his own program. So this is also super severe because you have a machine which is supposed to do something and you remotely as an attacker, you take control and you replace basically the program executed by the machine. So you hijack basically the production. Then again, in another attack, it's about how to damage the piece that get produced. Here we abused what's called automated advanced management tool. This is super cool. So when you have a production line that goes 24/7, so you are producing constantly. As I was telling you before, the tools get wasted. So they get, if it's a driller, they get lower, then the point is basically burn out. So the system what does automatically change the tool. And this one is made by this advanced management tool system. You can see here, this machine is configured with tool number 2, 10, and 15. And here you have this next tool. So that machine is configured in a way that after a certain amount of holes or after a certain amount of minutes that is operating with the tool and so on and so forth, different parameters, I don't go in detail, the machine changes the tool. Here you have basically the lifetime of the tool. So when the machine operates, you can see that the tool is getting wasted. Here an attacker can reset that value for the tool. So it can connect in and loop over and say, you know what, tool number 2 never gets exhausted. It's only 100%. Continue like that. So the machine doesn't change the tool, continue to drill with the same tool or operate with the same tool, damaging the tool and the part, which costs a lot. So this is like super severe as well. It's a denial of service attack that can burn like $100,000 easily. This one is as well pretty interesting, and when I saw this one, I said, okay, it's really problematic. So this is like that's the controller, right, and that's the machine. So there is this nice button called feed hold. It's in red. So I was new of the CNC domain, so I didn't know what was a feed hold. They told me, you know what, it's like a brake of a car. So if there is a problem, the operator press a button, and the machine halt immediately. Okay, it's like you're driving. Okay, there is a problem, you brake, and something. Stop, no? It's like this one, emergency stop. So there is a feature which is undocumented that basically says that there is a way to disable such button from operating. And the problem here is that since there is no separation of duty, you can basically write to memory addresses that control such functionality. So we were able remotely to basically disable this feed holder. And so the machine is running, the operator press the button, but the button does not stop the machine from stopping. So the machine continue to work. So it's basically like an attack in which you say, you know what, I attack a car remotely, and when the driver presses the brake doesn't work. So it's exactly the same thing. Of course, this one got patched immediately because there are some nasty problem with that. This one is instead how you can still manufacture information. So here there is an operator. This is a colleague of us, operating this nice Okuma machine. So this is a real world machine, big from here down there to the end. So here we managed to, start monitoring. So we can monitor what the machine is doing. So if you are like criminals that is doing like targeted attacks or espionage, industrial espionage, you can dump information like this. The name of the machine, the serial number, which type of controller the machine is running, which kind of program is running. You see here the program is stop. Here the program start running. These are the instruction currently executed. So instruction 75 with this code, instruction 76 with this line of code, instruction 77 with this line of code. The program run. Here you can see that the one piece has been produced because you see the counter increasing. So a criminal can basically spy on production lines and dump all that stuff. Criminal can also trigger software alarms. So this is also pretty cool. So there are alarms such as, okay, you know what? The oil is low, like in your car, right? Or whatever. Like there are some real physical alarms. And then there are software alarms like in software, where I don't know why there is this feature with G-code, but you can basically trigger a software alarm. And of course, an attacker, we were able to trigger a software alarm remotely. So when you trigger such software alarm, the machine goes in panic. It gives, you know what, there is an active alarm, and at that point, the machine stops, and the attacker and then the operator need to restart the machine. We're almost done, I guess. That's an example how you could ransom the machine. So that one is basically, you use Visual Basic and you basically screen lock, which is an Okuma. And of course, the operator see that, your ECNC has been compromised and locked. So discussion about this is that CNC machines are very complex systems and they open the door to an attack surface which is huge. And this research we conducted is, again, I think only the point of the iceberg. There is a problem with the fact that the supply chain is super complex. So if you talk to the NC vendor, sometimes they tell you, okay, you know what? It's a problem to the manufacturer. And when you talk to the manufacturer, they say, no, it's a problem to the reseller of the integrator. So there is a shift of responsibility along the chain, which does not help. There is a problem that if there is, as I was telling before, a bug at the beginning of the supply chain, the bug gets propagated, and even worse, since there are a stack of software that get added on top. So, as I was telling you before, Okuma allows, for example, to add to the CNC machine plugins, like applications, like third-party applications, so you can understand what goes wrong when you add things on top, right? So more complexity, more problems. And then patch deployment is still a major issue here, because as in generally in the ICS space, it's not as easy, to do patching. So some words about responsible disclosure. It was long and sustained. So it's not like you guys find a bug in Apple and they have like a program for that and they have security experts. Here we're still very far from being there. So it took us a while to explain the problem, to communicate our findings. So at the end, this responsible disclosure became more like doing some teaching or explaining them. So we are basically acting as consultants to this vendor. I have to say thanks to, I'm not sure if you ever work in the ICS space, but CISA does a great job. Similar as ZDI does a great job with a traditional vendor. These guys from the US, it's a US security agency. They are very collaborative and they provide a super support for interacting with a vendor. At the end, pretty much all the problems here have been fixed or they will be fixed. So we are on the good way here. some countermeasure, because as I was telling you, patching is a kind of nightmare. So many people ask me, okay, what can I do while I have my machine installed and potentially exposed to problem? Is, of course, use some standard techniques here, which could be like network segmentation, which kind of obvious, but often is not the case. Or often you use industrial gateways that contain themselves vulnerabilities. So we have done a work 4 years ago where we exposed bugs in industrial gateways. So if there is a bug there, then you can easily get access to this segment. And consider this machine then as important as traditional machines. So they come with a bunch of software that can have issues. So you should include this machine in your assets when you do testing of security problems. And when you buy also machines, maybe consider security as an important feature. So I know that usually people go for the cheaper like equipment, but especially when you deal with machine that cost easily 100,000, even more, or also $1 million. I mean, consider security on top of that. So this is just a summary of what we did. I have a bunch of videos that I put online, and we also wrote a paper which is something like 80 pages long that contain all the details of attacks that I couldn't go in here otherwise. It's going to be long. You can Google for it. You can find it online. There are also videos of different attacks, how you could do a denial of service of the machine, how you could dump and leak information, how you could hijack the production or damage a machine. So if you want to know more, you can find everything online. Thanks again for your time. With this, I conclude. I'm open to questions if we still have time, and I'm also reachable online via email or Twitter. Thanks a lot.
All right. Thank you, Marco. I think we have plenty of time for questions. So if there are questions in the room, please raise your hand. I see a question over there. The mic will come to you. It's to your left.
Hi, Marco. Thank you for talk. My question is related to, have you attempted to do full internet scanning to find out if any of these controllers exposed to the internet?
Yes. So I went, is it recorded? Also the Q&A?
It is recorded.
Okay, yes, we did something in that direction, and there are some issues you can easily guess, especially because Shodan, to name one, does not support all the different flavor of proprietary protocols used by CNC machines. That means there could be even more machine of what Shodan can tell you because it's not able to test them. So if you want to do a very accurate analysis, I suggest you use something like ZMap and write your own, basically, testing modules for testing things. But yes, one issue is that, of course, we are connected to the internet. There could be more of what traditional online system can tell you.
Okay. So the attack surface mentioned in the talk implies that you have to be on the network.
Yes, I mean, all the attacks are remote. Yes. I didn't have a slide about threat modeling, but all the attacks are remote. So you should be able to connect to the machine. So either you are in the network segment of the machine, so in the production line, right? So if you take the example of Stuxnet, you have like machines that were connecting, right? Okay, so either you are in that segment, or there is a misconfiguration, and from enterprise you can pivot down to the production line, which is often the case because this machine communicates with the ERP, which is called the MES. It's basically the system for managing the production. So there is often a connection between the enterprise network and the production network when it comes to monitoring what the production line is doing. And a bunch of machines come with a SIM card, right? Like cars nowadays, they have like an embedded SIM card for communicating to the internet. And that can, open the door to people basically connecting from the internet.
Okay.
So it's pretty scary, yes.
Thank you.
All right, we have another question here at the front.
All right, thank you, Marco. All those proprietary protocols that you have seen running on those machines, do they have a public documentation on how they work, or did you have to reverse engineer them?
What's your guess?
You had to reverse engineer.
Exactly.
Right.
So here we are still in an area in which security through obscurity. So I was kind of lucky because having collaborated with these guys, reseller, which is if not the largest, among the largest resellers of CNC machine in Italy. Since you are a partner with a vendor, you have access to certain documentation, not everything, but let's say that was a kind of gray box, our analysis occurs. If you don't have access to someone reselling CNC machines, it's completely black box.
All right, thank you.
So all the technology here is black box. So if you Google for it, you cannot even find, if you Google for the term, there is nothing. Okay?
All right, I Googled it and I couldn't find anything, so thank you, Mark.
Exactly. You should be already in contact somehow because you are collaborating with a partner. So at that point, you have access to some documentation. But again, it's security through obscurity, so there is a lot of work on reverse engineering propriety, not only protocols, but also software.
Thank you.
Do we have more questions? Because I do have a question also.
Yes.
So you mentioned a few protocols
Yes.
where a few of the attacks were very inherent in the protocol, like reading data, writing data.
Yes.
How do the manufacturers solve those problems? How do they fix it if it's already embedded in the protocol?
Yes, so there are some features that we manage to abuse, and the thing is you can abuse of such features because there is no separation of duties of memory. For example, you can write outside of a memory address of a program that gets executed. So that one is a limitation of the operating system, of a sub-layer of the operating system. So the fix is on the architecture of this sub-layer of operating system. Another fix is authentication. So some vendors do not support authentication at all on these services, which is super scary. Others do support authentication, which is sometimes brokered for different reasons, or is not enabled by default. So some vendor enabled by default authentication where it was not enabled by default.
All right, thank you. If there are no other questions, and I would like to thank Marco for his talk.
Thank you.
We are going to take